There's been some feedback on the previous video. Some of the measurements were not accurate. For instance, it was definitely an 8-axle B train, so this mass that I used, far too small. In fact, this is the picture of the actual truck, and somebody's able to read what's stenciled on there. And the mass of the B train, if it was fully loaded, 100% capacity, should be 63,500. That's its GMVR, gross, whatever. Fully loaded, that's its maximum. And notice where I had it before, about 80%, that makes for a high semi-speed. But if I give the truck more mass, it slows it down accordingly. The other question was the mass of the bus. So on this website here, here's the website I used. There's the bus, very similar. Curb weight says that it's a ordinary vehicle. It's got all the seats. It's got the motor oil, the coolant, air conditioning, so on. Sometimes a full tank of fuel, but it's not loaded with passengers or cargo, so it's sitting there empty. Nobody's on it. That would be 35,100. It's GVWR, fully loaded, 48,000 pounds. So I've entered that in here too. This is changeable. If it's an empty bus, 35,000 pounds. If it's a full bus, 48,000. Now notice what that does. Much over here to the calculator. This is identical to the previous one. I think I changed these vectors a bit. Identical to the previous one in terms of the formula. Okay, but if we make the bus lighter, then the semi-speed goes, I wanted 50, goes accordingly lower. Now that bus can hold like 55 passengers or something. There was only 30. Each boy would have a hockey bag, but it's not that heavy. They carry it themselves. There'd be some extra sticks. I don't know, 45% capacity. I mean, the lower I make it, the better it is for the semi. If I go down to 10% capacity, which is unrealistic, it helps let's just say 40%. I don't know. Trying to be fair to what we do to the speed of the semi. Okay, now the other point raised was that this might be unrealistic. I mean, if you have the bus speeding, it's worse for the semi. But we do know from eyewitness accounts that the bus driver said, whoa, and he slammed on the brakes. So how much did he slow down? Did he slow down to 80? See, that makes a difference, doesn't it? Did he manage to slow down to 60? And see how you can get a different range of results here. So some people wanted more precision. I can't give ultimate precision that the those investigating would result in. I can't do that. But we can get a little bit more precise if that's what people are asking about. We can be a little more precise because notice how I've got anywhere from 55 to 95 basically. And so some people are saying, well, that, it's not helpful enough. So I've got another whole piece here that was hidden just a second ago. I'll remove it. This has been added, and it deals with if the bus was able to slow down. So if its initial speed before braking was 120, but it was able to slow down to, see, if I can slow it down to 75, it's going to affect this. All right. And so whatever you think is a reasonable speed to begin with, there's another eyewitness that was actually sitting at the stop sign, said she saw the bus approaching at normal highway speeds. So I don't know, 110, maybe able to slow down to 75. So let's see with it. But this gives me a couple of different calculations that I can use. For instance, we can talk about reaction time. That's the time when your brain registers that you see something and you need to slow down, but your foot has to move over and press the brake. A good driver that's fully alert can easily achieve 0.6 or 0.7. A distracted driver, that could be very long. If he's texting, it could be 4 seconds, who knows. Okay, and what that does is that enables me to do a calculation here. If we're trying to slow down from 110 to 75, and there's this much time wasted before he even steps on the brakes, just in getting his brain to get his foot to move. That's a total time of 2.1 seconds. So I don't know if you can see in this calculation here. Oh, where did this acceleration come from? Let's talk about that. There's a braking distance calculator. And if you just type in different speeds, like at 100 kilometers per hour, it takes 56.23 meters to stop. At 110 kilometers per hour, it takes 68.4. So I typed, like, here's 110, 68.04. Here's 156.23. And it calculated out right there. That's an acceleration. It doesn't matter which one I pick. It's acceleration of about negative 7 meters per second squared. And someone else gave me a link to an article saying that larger vehicles have very efficient braking systems, and they can achieve the same rates as a car does. So whether it's a car, whether it's a bus, this is for dry pavement conditions, which was what was the case. There was no snow on the road. So this is a reasonable number to use. And using that number, we can then calculate that during the 0.7 seconds while his brain is aware but his foot hasn't reached the pedal, it's uniform motion. And then during the next few seconds to slow down from 110 to 75, it's decelerated motion. The bus would travel, on this scenario, 70.5 meters. And I can use that 2.1 seconds to determine how far the truck would travel using this 69.9, which it is currently, and the 2.1 seconds, I can determine how far it would go. Okay, and so then what that does is that enables me to see about reasonableness. So if this is from there to there, well, I went too far, not 80, see, I'm using the path, 86, I want about 70 meters. Somewhere around there. Okay, and what did I say the truck travels? 40.7. Okay, so just in line halfway with this roof, and 40.7 is there. Okay, so what I'm asking is, can they see each other? Because it's not reasonable for the bus driver to step on the brakes, to slam on the brakes, unless he can see. So I was down here before. Let's see, that's getting messed up. Let's do it like this. Okay, so let's clear this one off. Okay, so that's about 40 meters. And this is about, okay, 40 right to there. And then 70 was down to here. So can they see each other? And this shadow is for this tree. So as long as that tree is not in the way of that line, then they can see each other. Got a better diagram over here. So there's the triangle. There's the tree. Sorry, there's the shadow. There's the tree. So I can do two triangles. I can do a small one from the bus to the tree. And whatever, I can calculate that angle here because I can do all these measurements on Google Earth. And I can calculate that angle. And then I have a similar triangle that's larger. And it'll have the same angle. And this is easily calculated from the tree to the point of impact. And then I can compare with the distance that I just calculated for the truck. And if he's smaller than this distance, okay. But if he's back here, if the truck is over here, then we have an unreasonable situation because the bus would not slam on the brakes when he can't see the truck. Now, if the truck is here and the bus is here, then it's reasonable. He would see it. He would slam on his brakes. One thing to point out, though, is that, like this is a B train. The bus did not hit the front of it, so I have to add. It's about 9.5 meters I calculated for the tractor to get from this point to this point. Okay, it's about 9.5 meters extra. All right, so that's reasonableness. And that's what I've got here, the small triangle and so on. There's the angle. That also gives me, so not only have I got that one check about can the bus actually see it, and if he doesn't, like this, I have it, it'll determine if it's reasonable or not. There's a way that it'll say error in this formula here. So at that angle, it's good. Okay. I've got another correction or check as well in this calculator, because previously I said using this 2.1 seconds, the truck goes this far. But now I've got a triangle for the truck. And obviously these two distances need to agree. How can one calculation say the semi is traveling 40 meters when the other calculation, that triangle that I just showed you, has the truck, see with this 9.5 meters extra, has the truck going 60.5 meters. So I've got two checks for reasonableness here that will hopefully help improve the situation from before. And then we can just play with it and see what results we get. Another thing I should mention, these vectors, I changed them. If you look here, I drew in, this is the debris. And so from the skid marks, which is like right in the southbound lane here, you want to hit the center of mass. So the tractor has a lot of mass. There's all this bales of peat moss. Each of those bales, there are 3.8 cubic feet of peat moss compressed, and it weighs 60 pounds. So there's lots of them here. This is the front axle of the bus. This is the engine of the bus. Not much mass here because this is just the cargo or passenger area of the bus. So the X component of this vector, this displacement vector, you want to kind of hit the middle. This is much more accurate, and these ones here, I used overhead aerial pictures, and I changed the angle of Google Earth to get these. I used several different pictures, and whatever angle the picture was on, I duplicated that in Google Earth. Pretty certain that these are close. So, I don't know, go about there for an X. So notice it's about 41.4 meters. I got 41.5 here. I can shorten this up a bit. I don't know. 44, let's go with 44 then. What did that do? See, the problem is that makes the semi. So let's keep it small so that we're being fair to the semi, because the bigger I make this, the faster it makes the semi go. So I think I don't know, 40.5 is reasonable. Let's just go with 40. Let me just check here. Let's move the skid marks into the southbound lane. Is that the center of mass? I don't know. I think I need to go to 41. 41. Okay. The X vector, I'm going to use 41. The Y vector, $12 meters, just in the middle there. Okay. So we're going to go with, what did I say, 41 and 12 meters. What if I change it to 40? Just to be fair to the semi. Let's just use 40 and 12. Okay, so then I'm going to stop here and do a part 2 where we play with those numbers and see what we can get. Scenario 1 then, let's look at is if the semi driver does not see the stop sign and goes through completely unaware at highway speeds. So we want, I guess there's no reason to think that the semi could be over capacity. I mean, that slows it down. So let's even put it at 95% capacity. I don't know, 100% capacity, whatever. Bus load, a heavier bus speeds it up. Let's suppose, I mean, they are 29 young boys, but they're also hockey players, so they're physically big boys and they're hockey sticks and stuff. Let's say 55% capacity. The bus speed at impact, I don't know. All right, I'm trying to get this number close to 100 kilometers per hour, just to see what type of scenario we would have. So I don't know. Maybe the bus doing 110. Does that make it worse? I'm trying to get these numbers now to work. Notice if I put a reaction time of 0, then I get an error because he's got 29 meters to go and his triangle's only 20, like it doesn't work, right? So I have to have something there that mathematically doesn't give me an impossible triangle. All right, so these don't match at all. How can I get them to match? If this is doing 110, that makes it better. 0.6 makes it worse. 1.1, 1.2, 1.3, getting closer. So I would like this to be like the 0.7 because that's where a good driver that's alert should easily be able to get 0.6, 0.7. But if we can't get it, we can't there. That's really close. 53 and 53.7. Okay, so with a driver reaction time of 1.4 seconds, the bus going from 110 to 95, the B train fully loaded to capacity, the bus 55%, we can get a speed of 95.5 kilometers per hour for the semi. Now I want to go to Google Earth and I just want to show you the bus would travel 90 kilometers and the semi would travel 53. So let's clear all of this. So the bus would travel, what did I say, 90 meters? Like that. And the truck driver, 53 meters. And both of those match, so it's mathematically plausible. And the tractor, because the first trailer is hit, the tractor's here. So when I'm doing this 53 meters, okay. So notice how that triangle just misses that tree, right? So 50, if he's 53 meters from where the tractor is located there from point of impact, and if the bus is 90 meters from point of impact, then they could see each other. It is reasonable to assume that the bus driver with his reaction time of 1.4 would say, whoa, and he would move his feet to the pedal and he would push on the brakes and they would slow down from 110 to 95 and the impact. And this is scenario A with the semi driver completely missing the fact that there's a stop sign there and going straight through. The evidence for that would be that the skid marks left by the semi are in this lane. There's no evasive action whatsoever by the semi driver. Okay, seems like a pretty reasonable scenario to me. And those are the numbers that you can get. Approximately highway speed. Let's check out some other scenarios and see if we get something different. All right, scenario 2, let's try to see how low we can get this speed of the semi, and then we'll use our check for reasonableness and we'll also look at it and ask ourselves. So the slower the bus goes, just watch this speed here, 82.9. If I decrease the bus speed, that gets down. So let's have a slow bus. The lighter the bus, the slower the speed, not much though. And the heavier the truck gets slower. Let's really load it on. Okay, that's down to like 36.5 kilometers per hour. So that would be the scenario where the truck sees the stop sign, sheds most of its speed going at 36.5 through the stop sign, but the trees are the problem and it doesn't see it in time. Okay, now down here to my reasonableness checker, these two numbers need to agree. So does that help? 23.6, that made it a bit better. Let's work with the driver reaction time. Whoops, 1.9 seconds. It's getting close, 2 seconds. 2.1, let's do 2.2. Wow, okay, I've got it to agree. 46.5, 46. Okay, so this is mathematically, this is a realistic scenario, mathematically. And we can get the speed going as slow as 36.5 kilometers per second. We have to have, this is a problem for the bus driver, 2.2 seconds. For a professional driver, means he's not at the level of alertness that his employer would expect. So he's obviously either looking at his cell phone or visiting. 2.2 seconds is not an acceptable reaction time. Now, what does that mean though? Like, look at the distance the bus travels. 153 meters, and the semi only goes 46. So 153 meters. Oh, it's way off the screen. $153 meters. Down to like the middle of this shed here. 153 meters. And the truck is going 46.5. Oops. So just at that shed, but the truck 46.5. Something like that. And it should just squeak by that tree, and they should be able to see each other. That 46.5. Oh, that's from the tractor, so I got to move it over. The tractor's out here, 46.5. Yeah, so when let's change this to path. The tractor goes from here to here, and the bus is down here. Yes, it just clears the tree. Okay, there's a kind of have a concern with that scenario though, even though mathematically it seems like it works. Problem is that you've got a truck. He has to take some responsibility for what he's looking at too. And especially if he's only going 36.5 kilometers per hour. There's a bus coming from here. And you'd think that the driver of the truck could look way down here, see a bus, and come to a stop or at least turn or something. But if you look at the skid marks, he went straight. No evasive action whatsoever. And traveling at that speed, now we've got something that, even though it's mathematically plausible, it just doesn't ring true. Because this yellow line, and he can't see it for that whole distance, the slow speed that he's going, and just trying to turn or something. We do know there's a witness that came forward that was interviewed on CBC that was sitting right at this stop sign. And she said, she didn't give too many details because of the investigation, but she said the bus was approaching at highway speeds. She was aware of the bus the whole time. So the truck driver, to go from this 46 meters, not to be aware, not to make any evasive action at all. Now we're into, even though the math works, I don't buy this. How could a truck driver be completely oblivious? We've already established that, I guess perfect storm, that the bus driver is distracted or on his phone or something or visiting. But how could the truck driver not see it? Especially going so slow. Okay, That's it for scenario 2. Let's try scenario 3 where we don't have the truck going so slow. Maybe he rolled through, but it was 60, 70 kilometers per hour. That'll be next. Okay, scenario 3. Let's try to get this in the 60, 70, 75 range. So we can bring that's like, this is way unreasonable for the bus capacity. Let's have it there. This is too low for the truck capacity, 110. This is too low for the bus. We can put the speed up a bit of the bus. All right, 65. Let's see if that's reasonable. And the bus, maybe doing 110 to begin with. Okay, driver reaction time. Okay, I'm trying to get this 65 to match with this 47. So let's try 1.7, 1.4. Okay, that's very close. Okay, so we've got a mathematically plausible result here that seems to cover most of what people's comments were, that I need to slow the bus down because we do know that the bus driver said whoa and hit the brakes. We do need to work on the masses. So there, I think I've addressed both of those issues. We've got a semi-speed at a not highway speed, but it's a rolling stop, even though it's a fairly swift one. And all my mathematical checks work out. So this could work. So now let's look. Driver reaction time is a bit better than it was before. 1.4 seconds. It's not completely terrible. It should be better than that, but we don't have to, say that it was a distracted driver. Just maybe it might have been checking the mirror before he looked frontwards. Okay, and I mean in total it's only 2.8 seconds from the time he says whoa, then steps on the brake, and then the impact. Okay, so let's go look at that. We have bus going 101 meters and truck going 51 meters. So bus going 101 meters. About there. And truck going 51 meters. And the truck has to, the tractor has to get through the intersection because there. And if I connect these up, it just misses that tree, so that's good. Okay. And again, you have to ask yourself, if the stop sign is here and he's going 65, the bus is still a long ways away. You'd think that if you're going to, as you said, aware of the, as people had commented said, aware of the stop sign and slowed down to 65, but did not look this direction at all, because skid marks from the truck are straight here with no sign of turning whatsoever. No effort to make evasive action whatsoever. That's a long distance for this truck driver to, in a somewhat responsible way, slow down, but in an otherwise completely irresponsible way to not look to his left. No evasive action whatsoever. At 65, you'd think you could do something. I don't know. Let's go back and maybe a little bit faster. Let's try to get this to 70 or 75. So if we have a faster bus, 74, let's get a little faster bus yet. There we go. 75, okay. And these numbers, maybe I can make them agree a little bit better. not sure if I'm making it better or worse. That's pretty close. 1.44 seconds, that's pretty close. And that's not bad for reaction time. Okay, mathematically plausible. Semi going 75, bus slowing down from 110 to 85. I could have the bus going 100 too, but that makes it longer here. Let's see here. If the bus is doing 110, let's have the bus only doing 100 because it makes this not so long. So 1.85 maybe. Those are pretty close. Okay. So bus doing 100 slows down to 85, semi doing 75. This is all mathematically plausible. That gives us a distance that the bus travels as 90, basically 100, and the semi 52. Okay, bus 100. Oh, that didn't change much at all, did it? Bus 100, semi 52. Oh, that doesn't change much, does it? So now we're in the situation where the slower I make the semi, the longer this gets, and marginally shorter this gets. But also, if he's going so slow, why couldn't he make any evasive action and go straight through and have skid marks from here to here? And then if I speed the semi up, this gets shorter, but this doesn't get that much longer. And I mean, we're now at 75. That's almost highway speeds. It's not really a rolling stop anymore. It's slowed down a bit, but not a rolling stop. So I don't know. I have, based on the feedback left, I have worked with these numbers. I've added in some check for reasonableness, but I don't think that these measurements support a truck doing anything slower than 75. And I think that these measurements do in fact indicate that the bus was going anywhere from 75 to 95. It would be interesting if I could find a way to share this spreadsheet, maybe on a link where it could be downloaded, and then other people could play with it and see if they could get better results. I mean, certainly you could change this X and Y vector, and all of these other numbers that are in blue are changeable. While it's just dealing with some pretty general measurements, I think the results from this are fairly accurate, even though it's not intended to place blame on anybody, and it's not to be confused with the actual investigation that's going on. Last consideration, I've made a number of assumptions about the bus driver not speeding, the bus driver having a good reaction time, and so on. Okay, now the father of one of the Broncos, Mr. Thomas, was quoted as saying that the RCMP told him that the semi-driver went through the stop sign and said the sun was in his eyes. And there's been lots of debate about, is the sun in his eyes or is the sun not in his eyes? Even Mr. Thomas said that there's no way. It's 2 hours until sunset. The sun is not nearly low enough to be in his eyes. But it doesn't have to be sunset for the sun to be in a person's eyes. So let's just explore that and see what we can come up with. So first thing is you can visit this. The link is here, suncalc.org. I've typed in the exact latitude and longitude of that intersection, and I've typed in the date and the time. And the time zone is Regina, it says CST. So you can see here that There are the coordinates for the intersection, latitude and longitude. It comes up as RM of Connaught. There's the date, April 6th. There's the time, 5 p.m. Saskatchewan never changes for daylight savings, so some of the time we're UTC -5, sometimes -6. This is the current one for that. That says Regina. All right, so these two numbers are what you're going to get. 22.86 degrees is the altitude. Now, if I mouse over, it says it's the angle of elevation. It's not angle. So in other words, if you put your hand straight up, that's a 90 degrees elevation. If you put your hand straight out in front of you, in a horizontal, like parallel with the floor, that would be 0. So to get to 22.86, let me just bring up a picture here if I have one. Where do I have it? Right here. Okay, so this is the actual truck. All right, so let's just pick a spot for the eyeball of the driver. I'm going to hold my shift key so that if I don't hold shift, I can get all these angles. But if I hold shift, I get exactly 0. Okay, so that's an angle of elevation 0. So hopefully I've got the right spot for his eyeball there. This would be an angle of elevation of 90. Now I can also hold shift, see how it's all these different angles? I can also hold shift and get 45. So what we have to do to get, what was it, 22.86? Pretty close to 22.5. What we have to do is bisect. So, and I'm just eyeballing this. I don't know. Now you can see that this truck has a visor, an external visor. But again, who knows if I've got the driver sitting back far enough. Maybe I need to move it forward a bit. It doesn't look like the sun should be a problem. 22.86 degrees. Okay, let's go back to this. No, this. The other information that it gives you is the azimuth. So I can mouse over, but the easier way to say that is 270 degrees. Like if you count in 90s, you get through all the quadrants, 90, 180, 270. Okay, 270 degrees would be due west. So it's not quite due west, but it's almost due west. Okay, so it does give, if the sun wasn't directly in his eyes, it certainly was low enough to be in a nuisance, and he was driving directly towards it. We can also find this on Google Earth. If we click here on this sun thing, and I'm going to click on the tool here, I want April the 6th at 5 p.m. and I'm in Saskatchewan, so I'll use the time zone on my computer. All right, April the 6th, 5 p.m. Now it's actually going to show me the sun. I got to get down to ground level. Let's go here where the semi is approaching. Okay, it's not street view, but there we have it. So, driving down this road, and you can see I've got some things marked ahead of me. Oops, got a little bit crooked there. Driving down this road, there is the sun. Exactly at that position. 22, if there's an angle from, like a right triangle here, it's 22.86 degrees up in the sky. 270 degrees would be due west right here. It's a little bit over here. That's what the semi-driver was driving into. And that completely corroborates these results. So the sun, if it wasn't causing him, making it impossible to see, it certainly was causing difficulties. Is that an excuse? Absolutely not. There's a stop sign. The stop sign has, I don't know if you can, I got to get out into street view. The stop sign, if I get to street view here, you'll see it from the other side. There's no street view on this side, on the one side. Okay, gotta turn around here. So you see that stop sign? It's got a beacon. It's not amber, it's red. It flashes red. How do I get closer? There. You can see the stop sign. You can see the red flashing light. There's an identical one here. Now it's kind of close to the road because it's on the light pole. It's like right up to the road, but if you have the sun in your eyes, there was snow. On this side, the snow was about this deep. On the other side, the snow was not quite so deep. But besides that, besides the stop sign, if you go back, and this is the same on both sides of the intersection, there's also a stop ahead sign. That's a significant distance here. Oh, there's a junction sign. Now I've seen some intersections that have a much bigger sign than this, and it says important intersection ahead, and then they would have rumble strips. This doesn't have it. There's two signs. That's just a highway sign. So I've got a stop sign. We've got a junction sign. And to go a little bit further back, there's the stop ahead sign. That's all the signage there is. You can see the stop sign, you can see the junction sign, you can see the stop ahead sign, and the stop sign has a flashing red beacon. And it's the exact same on the other side, even though there's no street view, so I can't show it to you. But that's what it looks like. Let's see, let's count the distractions. So we've got miles and miles of nothing. There's an elevator. There's trees. The sun's in his eyes. I guess he's missed all the signs. There'd be a stop ahead sign. There'd be a junction sign. It's small. There'd be a stop sign right up against the highway there. Over here there would be there's a railway ahead sign. There's a railway. There's another. This is Bungie, another plant. And here's the second railway. So as the driver's approaching, he might be looking ahead and seeing those things, or just hiding his eyes from the sun. I'm not sure. But it is hard to tell that there's a road here, because even though this is a secondary highway, 335 is a secondary highway, and 35 is not. But they're the same grade. They're the same distance above the surrounding landscape. And with snow on the edges, when you're driving this way, if there's no traffic coming, you might be completely unaware that there's an intersection. So, is the sun an issue? Perhaps, perhaps not. It shouldn't be a factor, though. When you are driving and you're a licensed driver, you can't use excuses as sun was in my eyes. If the sun was in your eyes and it was unsafe for you to proceed, you should pull over and wait until the sun is no longer in your eyes. Or, try your sun visor, try your sunglasses. But don't continue driving if you can't see.